Welcome to Chapter 4. In this chapter, we're going to be exploring the concept of exponential and logarithmic functions. So there should be an element of review. These are things that you should have seen in algebra or even pre-calculus. But we're also going to be then tying these concepts and these types of functions into our calculus concepts like with derivatives. So let's get started here in 4.1. We're talking about the exponential functions. So an exponential function has the form f of x equals b to the x, where b is a positive value that is not equal to 1. We say that it's not equal to 1 because that kind of makes it trivial, because anything raised on a power where the base is 1 would still be 1. So that doesn't really give us useful information. And x is a variable. So notice that these are different from power functions. So a power function was something that looked like this, like x to the b, whereas an exponential function is b to the x. So the location of the variable is what really separates these two. So a power function, the x is in the base, but the exponential function, the variable is in the exponent up there. These are two very different types of functions. They behave differently from each other. We're going to be looking at some of the behavior of these exponential functions and then looking at some examples dealing with these. So first off, we're going to start with a couple basic exponential graphs. The graph of 2 to the x and 1/2 to the x. So for 2 to the x, if we pick some x values, so like if we pick x equals 0, we get 2 to the 0 is 1. And that 0.01 is going to be on every exponential function, assuming that it's not like shifted anywhere. Then we move, when x is 1, we get 2 to the first, then 2 to the second, 2 to the third is 8, 2 to the fourth would be 16, so it's way up there. If we go backwards, 2 to the -1 is 1/2, so that's down there. Then 1/4, and then 1/8, and then et cetera, et cetera. So it's going to get really, really close to that x-axis. So if I connect the dots as smoothly as I can, should get something kind of like that. So you can see that the values are very, very flat for a long time. And then once we get into positive x values, the values skyrocket, right? This is what we call exponential growth. So it grows very, very quickly once you get past this point. On the flip side, if we have g of x, which is 1/2 to the x, we still get the point 0, 1. But now if we plug in x equals 1, we get 1/2. And then x equals 2 gives us 1/4, et cetera, et cetera. This time, if we plug in -1, we get 1/2 to the -1. The negative power flips it. So 2 over 1 to the first is just 2. So like that. And then we get the same kind of thing. We get 4, then we get 8, then we would get 16. So we're going to get the same kind of graph, just flipped. All right? These graphs are basically just a mirror image of each other across the y-axis. So they behave very similarly, but they go in opposite directions, basically, right? This one grows very large as x gets bigger. This one grows very large as x gets smaller, as it gets more negative. And as x gets bigger, the values start heading towards 0, right? It starts flatlining to the x-axis. So if the base of the exponential function is greater than 1, then it is called a growth function. And like I said, this type of exponential function sees outputs increase as inputs increase. Okay, so x gets bigger, y gets bigger. That's what that means. If the base is between 0 and 1, so it's a fraction, then this is what we call a decay function. So this type of exponential function sees outputs decrease as inputs increase. So x gets bigger, but y gets smaller. And like I said, if you're dealing with a base that is 1, then it doesn't grow or shrink or decay because it's always going to be 1. And if you throw negatives into the mix, that changes everything. So we're not worried about negative bases here, only positive that are not equal to 1. Now, there are some exponential functions that come up more than others. And the most commonly occurring exponential bases that we work with is called the natural exponential base. Okay, so it gives us the natural exponential function. This number is the number e. So the number e, which I know if you're thinking like, but that's a letter, not a number. I know, but it represents a number. A specific number. It is an irrational number. The way that we define E, you can actually prove this using calculus, but the definition of E is equal to the limit as x approaches infinity of 1 over 1 plus x all raised to the x power. This would be like the precise definition of E. But it is an irrational number, so we can't come up with like a whole number value for it. So if you wanted to know approximately what this value is, it's about 2.71828, and then et cetera, et cetera. So it's irrational, so it goes on forever and does not repeat. But it's approximately 2.7. Right, 2.72, roughly. This number comes up so frequently and has the most helpful properties of the exponential functions that we're going to be working with this one a lot, probably more than any other exponential function. The nice thing is that e to the x does behave like all the other exponential functions. So this provides us with a useful general exponential function. So that's f of t equals a naught times e to the kt, where a naught represents an initial amount or quantity. So that's like our starting amount. T represents time, and k is a number known as the growth constant, which tells us proportionally how quickly the value grows. So the growth constant is something that we can find, and we'll do plenty of examples working with it. But it gives us an idea of how quickly the exponential function is growing or potentially decaying, because if we want to predict growth, then we do use this version of the formula. But if we want to predict decay, it's the same formula, but we throw a negative in the power. Okay, that's going to make the values decrease instead of increase. So let's take a look at a few examples of these exponential functions, the e to the x functions. So I already have these set up here. So here's the graph of e to the x. So normal exponential function, right? I mean, if you look at like 2 to the x, like that, or 3 to the x, right? You can see E is roughly 2.7-ish. So it is between 2 and 3, a little bit closer to 3. So you can see it right there. It's a little bit closer to 3. But it just behaves like a normal exponential function. So we look at e to the negative x. Okay, we have same type of curve, but a reflection of the original. We have e to the 2x. So if we double the power, okay, see how it grows significantly faster. Okay, and then same thing if we reflect that. If you take something like a decimal, so raise e to the 0.3x, that's going to flatten it out significantly. So you can see it still grows with the same type of behavior, but much more slowly than the others do because it's being multiplied by that 0.3 in the power. And then same thing, we get a reflection of that. Now, when it comes to working with these exponential functions and the natural exponential function, e to the x, we have a few properties that we can talk about that are going to apply to all of these. So these are going to be pretty helpful for us to remember. The domain of an exponential function is all real numbers. So that's in our double-banded R there. So all real numbers are valid inputs of exponential functions. You can plug anything into them that you need to, and you will produce a valid output. The range is going to be all positive numbers. So this is like the interval 0 to infinity. Right? Because it does have a horizontal asymptote. We saw that with a lot of these here, right? It flattens out at the x-axis, so it's not going to be equal to 0, and it's not going to be negative. But its range can take on any of the positive numbers. And again, this is assuming that it's not like shifted or flipped or anything like that. As soon as you start transforming the function, that changes what the actual values will be. But we're just looking at the general function here. It is continuous. So getting some of our calculus terminology in here from chapter 1. Exponential functions are continuous everywhere. And it passes through the point 0, a naught. So I mentioned with the graphs earlier that they all pass through the point 0, 1, unless they are stretched or shifted. So if you have an exponential function, like e to the 0, something like that, whatever number is in front of it, right? So if I had like 3 e to the 0, e to the 0 is 1. 3 times 1 is 3. So we would get out the point 0, 3 instead of 0, 1. Okay, but exponential functions will always go through this point, and it just depends on what the coefficient is, the number in front is. And then we talked about this already, but growth functions increase as x increases. Decay functions decrease as x increases. So there are a lot of fields that can take exponential functions in as applications. So we're going to look at a few examples here. In a few different fields and see how we can start using exponential functions, particularly the natural exponential function, but we'll look at a few different types. So first example, a kitchen counter has 5 bacteria on it of a type that doubles every 10 minutes. The function a of t equals 5 times e to the 0.06931 t can be used to model the number of bacteria a of t in the population t minutes later. How many bacteria will be on the counter 2 hours later? Okay, so we have our formula. We put in a time. We get out an amount of bacteria, right? So we have the time, and then we have the number of bacteria is what we get out of that. The question is asking how many bacteria will be on the counter 2 hours later. So we're looking for an amount. So we're looking for a of t after 2 hours. Now you have to be very careful because if you go back and look at what t is, the temptation is to put that we want the amount after 2 hours, but that actually wouldn't be correct because t is in terms of minutes, not hours. So if we put in 2 to the formula, what we would be asking it is how many bacteria are there after 2 minutes? We don't want 2 minutes. We want 2 hours, which is 120 minutes. So we're going to take a of 120. So we get 5e to the 0.06931 times 120. And you'll definitely need a calculator to do these. This is approximately 20,468. Because after 120 minutes, and it's doubling every 10 minutes, that's going to be very, very quick growth. So we can say after 2 hours, there will be about 20,468 bacteria on the counter. One thing to take note of, make sure that you know what the question is asking for in terms of rounding. These problems almost always lead to decimal answers, right? Or irrational answers that you need to simplify or round. So this question in particular didn't ask for any particular rounding, but you can get questions that do. So make sure that you're aware if a question asks you round it to 2, 3 decimal places, only 1 decimal place, or if it just wants like the nearest whole number. Just be mindful of that because the online systems aren't always so forgiving on those kinds of things. Let's take a look at another example. When an initial principal amount of money P is invested at an interest rate R and compounded n times per year, the amount A accumulated after t years is given by that formula. So that's A of t is P times 1 plus R over n, all raised to the nt power. Determine the amount of money accumulated after 15 years if $2,000 is invested in an account that pays 8% compounded quarterly. Whew, that's a mouthful of a problem. So we got a lot going on here. Determine the amount of money accumulated. So we're looking for A of t again. That's our accumulated amount of money after 15 years. So that's t. $2,000 was invested initially. So that is the initial principal amount of money. So that's P. Invested in an account that pays 8% interest. That's R. Not exactly R, but we need the decimal approximation of that, which is 0.08. And then it is compounded quarterly. So when we say n is the number of times it's compounded per year, quarterly means 4 times per year. And that's going to be our n value. And that's everything we need to answer the question. So we're going to take a of 15 equals 2,000 times 1 plus 0.08 over 4 times, raised to the power of 4 times 15. So that gives us 2,000 times 1.02 raised to the 60th power. And that is approximately 6,562.06. So with these types of problems, you're often looking at kind of almost like puzzle piece style problems where it's like, here's the framework of the puzzle. Here are all the pieces that you need. Put them in the right places and then solve. Okay, so we just need to make sure that the pieces go in the right places in order to solve. And then with these contextual problems, these modeling problems, you always want to give some sort of conclusive statement in the context. Don't just box the number as the final answer. So we can say after 15 years, the $2,000 investment will grow to $6,562.06. Let's take a look at one more. Okay, so these types of word problems, these modeling problems, always look very intimidating. Try not to, freak out too much when you see the question or you see a formula that looks like this, that looks really, really messy. Because again, a lot of these problems are just asking you to plug stuff in. And so if we, just keep a level head, stay calm, and just figure out what exactly it's asking you to plug in or asking you to do and to solve, it's going to make it a lot easier on you. So let's take a look. So the number of automobile sales in a developing country can be modeled using a logistic growth formula. So that's this, with T greater than or equal to 2010. So 2010 is like our starting year, where N is the number of automobiles sold in 1 year, and T is the year. How many cars were sold in 2010? Okay. How many cars were projected to be sold in 2015? And then using this model, at what level will the sale of cars stabilize? Okay, so let's look at A first. How many cars are sold in 2010? Well, if we're letting T be 2010, so we get 156,000 over 1 plus 5.6 e to the negative 0.8, 2010 minus 2010. So this part gives us a 0. E to the 0 is 1. So we get 156,000 over 1 plus 5.6. And that's going to be approximately 23,636 cars that were sold in 2010. Part B, very similar. How many cars were projected to be sold in 2015? So it's basically asking the same question, just with a different year in its place. So we have our 156,000 over 1 plus 5.6 e to the negative 0.8, 2015 minus 2010. So that's going to be 5 times negative 0.8. That's going to be negative 4. So we get 156,000 over 1 plus 5.6 e to the negative 4. And this is a great time to just break out the calculator. No need to try to do all this by hand. There's no way. We would get 141,488 cars that are projected to be sold in 2015. Now, part C is where we bring in a little bit of our calculus techniques because it's asking a different type of question. So using this model, at what level will the sale of cars stabilize? So when we say that the level of cars of sales will stabilize, this is a logistic growth model. So it kind of goes something like this, where it grows really quickly and then it starts leveling off more and more, which kind of makes sense, right? Because if you have a brand new car that you're selling, you're going to sell a lot of them at first. It's going to grow really quickly. But then as more people already have the car, the amount of extras that you sell is going to get less and less and less as you go. So it's asking kind of, where is the cap? Where are we headed to as time goes on? We can answer this question using calculus by taking a limit. We're taking a limit as t goes to infinity. So we're saying as time passes, as time progresses, okay, for an infinitely long amount of time, we have 156,000 over 1 plus 5.6 e to the negative 0.8 times t minus 2010. So when we look at the exponential value here, t is getting infinitely large. That means that this power is getting infinitely large, but there's a negative in front of the power. So this is headed towards e to the negative infinity. So the power is getting infinitely large, but the fact that it has a negative means that it actually becomes a fraction, right? If we take the reciprocal of it. So that would be heading towards 1 over e to the infinity, and that's going to head towards 0. So we would get 156,000 over 1 plus 0. So we just get 156,000 cars. Okay, so that value that we were given in the numerator, that will be the kind of stabilized level. That's the kind of the cap, where they likely won't be selling much beyond that amount. So, but now we've seen a few different examples dealing with these exponential functions. So we've seen some biological, some business related, some social science. So now we're going to look at kind of the flip side of this in section 4.2 with the natural logarithm function. Log functions in general, you've probably encountered them in your time in algebra, but we're specifically going to be looking at the natural log function. This is related to the natural exponential function, e to the x. So we have the natural logarithm function, abbreviated ln of x, is defined as y equals log base e of x. So if you remember log base e, right, that would be like, or log base 2, log base 3, log base 4, whatever. This is log base e. And the natural log function is related to the e to the x function. So we say that y equals e to the x if and only if x equals ln of y. So the natural log function and natural exponential function are inverses of each other. Okay, so they do work against each other. They undo each other's effects, essentially. So ln of e to the x is just x, and e to the ln of x is just x. Okay. Domain and range are switched because they're inverses. So the domain of e to the x is the range of ln of x, and the range of e to the x is the domain of ln of x. And so it's always flipped. It's always backwards. So, for example, since e to the x will always be positive, the input of a log must always be positive. So I have the graph right down here. We have the e to the x graph that we worked with in the last section. We have the ln of x graph right here. Notice on the e to the x graph, we have the point 0, 1. On the ln of x graph, we have the point 1, 0. And there is a symmetry about these two. Because they're inverses, they're symmetric about this line y equals x. Because basically what we're just doing is switching the x and y's. Okay, so remember, domain is the x's, range is the y's. We're just flipping them, switching their roles. So yeah, that's how we get 0, 1 becomes 1, 0, and vice versa. Few properties of the natural log. These are the same as the standard logarithm properties that you would learn in algebra, just applied specifically to ln. So we know that ln of e is equal to 1 because e to the 1 equals e. That's kind of what this says, because this is like log base e. Ln of 1 is 0 because e to the 0 is 1. You can split ln of a product into a sum of ln's. You can split ln of a difference, of a quotient, so x over y, into a difference of two separate natural logs. And if you have ln of x to the r, you can bring down the r in front of the natural log. So these properties are going to be very helpful in simplifying a lot of our logarithms. This last one, I should mention, this property of like bringing down the r, people tend to get this mixed up with like the power rule, because we've talked about the power rule in calculus. This isn't the power rule. This is just an algebraic property of logarithms. We're not taking derivatives here yet. This is just something you can do with logs. You can also move it back up if you needed to. So let's take a look at some examples. Expand each expression. So we have here ln of a quotient. So we're going to go ahead and turn that into ln of 8x minus ln of x plus 4. And you can actually split this first one, 2, because that's a product of 8 times x. So we get ln of 8 plus ln of x minus ln of x plus 4. And you cannot split this one. So this is a common misconception. I think people get the formulas mixed up a little bit. You can only take ln of a product and split that into a sum. Ln of a sum, you can't do anything to it. Okay, so that one is not simplifiable any further. This one, we can split this, ln of x plus ln of y to the 5th. And then that power property, we can bring the 5 down in front. So we get ln of x plus 5 ln of y. We could not bring the 5 down here because the 5 only applies to the y, not to the x. So we can only apply the property if everything is under that power. Let's take a look at a couple more. So now instead of expanding, we are condensing. Write each expression as a single logarithm. So we have ln of x plus 6 ln of y. So I'll go ahead and move the power back up. So ln of x plus ln of y to the 6th. And then recombine into a product, ln of xy to the 6th. ln of a minus ln of b minus ln of c. So we're going to have some quotients here. So I'll do the first two. ln of a over b minus ln of c. And then that gives us ln of, technically it's a over b over c, but you can combine denominators like this. So ln of a over bc, like that. One of the primary uses of these logarithm properties is to be able to solve exponential equations. So if I have something like this, e to the 2x plus 5 equals 12, and I'm trying to solve for x, I can't solve for x if it's trapped up inside this e, this power of the e. So in order to solve it, I need to be able to get rid of the e. I need to get rid of the exponential part of this function, and I can do that using a logarithm, okay, a natural log specifically. So I'm going to take ln of e to the 2x plus 5, and whatever I do to one side, I have to do to the other. So I get ln of 12 over there. Now we can use that power property, so we can bring the 2x plus 5 down to the front. We have ln of e equals ln of 12. ln of e, if you recall, is 1. Okay? They essentially cancel each other, right? They undo each other's effects. So all we have is 2x plus 5 equals ln of 12. So 2x equals ln of 12 minus 5. So x equals ln of 12 minus 5 all over 2. And that would be our exact answer, and you would definitely just leave it like that so you don't have to worry about plugging it all in. If a question asked for a decimal approximation, this would give us approximately negative 1.2575. But as far as I'm concerned, the exact answer is better. Okay, we don't want to round if we don't have to. Let's throw a little bit of context into this. A piece of equipment depreciates according to the function a equals a naught e to the negative 0.32t, where t represents number of years since its purchase. A business has purchased a piece of equipment for $635,000. It will replace that equipment when its value is 10% of its purchase price. To the nearest year, how many years will the business keep that equipment? Okay. So a naught is the initial amount being spent times e to the negative 0.32t. The final amount is going to be 10% of its purchase price. So that's 10% of this, okay, of that number, the 635,000. So that's going to be 63,500. Which, if you do the division that's going to be 1 over 10 equals e to the negative 0.32t, right? Which 10%, that's 1/10, right? Or we can rewrite this as a decimal also. But now this problem just becomes exactly like the previous one, where we're just solving for the unknown variable. So from here, we can take ln of both sides. I'll rewrite 1/10 as 0.1 equals ln of e to the negative 0.32t. So we get ln of 0.1 equals negative 0.32t times ln of e. Ln of e is 1 again. So we just need to divide, right? So we get t equals ln of 0.1 over negative 0.32, which again, as an exact answer goes, that's great. This one, however, did ask us to round to the nearest year. So this is going to be approximately, if you plug it into a calculator, you get about 7. That's the nearest whole number to that value. I do want to make a note here, just as a side note for these natural log things. If you kept it as a fraction, you could rewrite this. And this is not something you had to do, but this is something you could do. You could use the log properties to split this into ln of 1 minus ln of 10. ln of 1 is 0, so you would get out negative ln of 10. Then when you do the division, the negatives would cancel, and you would have ln of 10 over 0.32, like that. And that would also be an equivalent final solution for this one. Okay, so there's not necessarily only one form that it can take, just depending on how you simplify using those log properties. All right, now we're going to bring some calculus back into this. In section 4.3, we're looking at differentiating the natural logarithm function. So we're just going to come right out with the definition, and then we can start using it. Derivative of ln of x is 1 over x. So that's the whole secret there. And this has a very nice, simple, concise formula. That's one of the reasons we like working with it so much, is because it is a very simple way of taking a derivative. So if we took a problem like this one, we have f of x is 7x cubed times ln of x, find f prime. This is going to be a product rule, right? You have two functions here. So we're going to take derivative of the first times the second plus derivative of the second times the first. So we get 21x squared ln of x plus 1 over x times 7x cubed. A little bit of cancellation here. So we get 21x squared ln of x plus 7x squared. So that would be our derivative. Now you can apply the chain rule to these derivatives, because like we said in the previous chapters, the chain rule applies to everything. So if you take ln of a function, so you have another function in there, not just x, the derivative is still 1 over whatever was inside. Okay, so that's the same. But then because of the chain rule, you have to multiply by the derivative of whatever was inside. so times g prime of x. You can also just condense this if you want into g prime over g. So either way works out the same. But this is going to allow us to take derivatives of stuff like these. So for part A, we have ln of 5x squared plus 2x minus 7. We 100% definitely need the chain rule to be able to do this. So if we get... So derivative of the natural log function is 1 over whatever was inside times now the derivative of whatever was inside. So that's going to be 10x plus 2 over 5x squared plus 2x minus 7. So that's the derivative of that natural log function. For this next one, we actually have a couple different ways we could approach this one. I'm going to show you both, but we'll just go at it with the formula first. So it would be 1 over whatever is in the ln, so x squared minus 4 cubed, times derivative of x squared minus 4 cubed. This, in and of itself, requires use of the chain rule. So the derivative of the cubic of that outer portion, that's going to be 3 times x squared minus 4 squared. So we did the power rule on it. But then we also need to multiply by the derivative of the inside again. So it's always possible that you can encounter the chain rule multiple times in the same problem. So that's not necessarily an issue. It's not a deal breaker for these problems. And then the derivative of x squared minus 4 is just 2x. So we have 1 over x squared minus 4 cubed times 3 times x squared minus 4 squared times 2x. So we'll get a little bit of cancellation, 2 of those with 2 of those. And we're left with 6x over x squared minus 4. For our final simplified derivative. Now, I did mention there was another way to approach this. If you consider using the limit property first, or sorry, not the limit property, the log property, this power is over the entire x squared minus 4. You can actually bring this out to the front using log rules. So we get 3 times ln of x squared minus 4. That's actually going to give us a much simpler solution to this. So the 3 just tags along because it's a constant multiple. We get 1 over x squared minus 4 times the derivative of x squared minus 4, which is 2x. We just did that one. So 3 and 2x is 6x over x squared minus 4. So we get the exact same thing, which that's the whole point, is that algebraically these two are equivalent, so we should be able to use the same calculus properties. And of course, get the same answer. Now, if we look at the last one down here, part C, we have h of x is ln of 3x all raised to the 4th power. This one is definitely a chain rule problem, but notice the difference between these two. In the previous one, the 3 technically is inside the ln here, That's what allows us to use like that property. This one, the 4 is outside of the ln. So the entire function is being raised to the 4th power. So if we want h prime, we're going to have to take the power rule first. So 4 times ln of 3x cubed times the derivative of ln of 3x. This is going to be 1 over 3x times the derivative of the inside of the 3x. So you can see how these chain rule problems, you're going to be kind of doing multiple layers like this. Derivative of that is 3. So we have 4 times ln of 3x cubed times 1 over 3x times 3. The 3's will cancel. So just times 1 over x. So there's not a whole lot more we can do to this. We can combine it, make it one term, but we're still going to have that all over x. So these are a few different types of examples of what you can see when you're differentiating that natural log function. To finish off the chapter, we're going to be looking at section 4.4, where we look at how to differentiate the natural exponential function. This is one of the nicest derivatives that we encounter in the study of calculus. It's, again, one of the main reasons we like using the natural exponential function so much, because the derivative of e to the x is e to the x. So the natural exponential function is a very rare function that is its own derivative. So the derivative of e to the x is e to the x. So it's always nice, not a lot to remember there. So we can try it out. So find the equation of the tangent line to the curve 7x e to the x at the point 0, 0. So let's get the derivative. So that's derivative of 7x is 7 times the e to the x. And then 7x times the derivative of e to the x is just e to the x. And all of these have a common 7e to the x in them. We're left with a 1 plus x like that. Now, this question didn't ask for the derivative specifically. It didn't even ask for the slope of the tangent line. It asked for the equation of the tangent line. So we're going to need a little bit more. So we're going to take f prime, evaluate it at 0. So we get 7 e to the 0 times 1 plus 0. That's 7. And then we just put in the equation of a line. So that's y minus y naught equals m times x minus x naught. So they made it a little easy on us by putting the point 0, 0 in there. We just get y equals 7x for the equation of that line. Once again, just like with the natural exponential function, the chain rule also applies here. So if you have e to a function up in the power, not just an x, its derivative is still the same thing again, but now times the derivative of the inside. So times the derivative of whatever's in the power. Okay. And sometimes you'll see it written condensed with the g prime in front. Doesn't really matter. For this one, let's find f double prime of x, given f of x is e to the 2x squared plus 5. So we're going to get f prime first. That's going to be derivative of e to the x, or e to anything, is just the same thing, times the derivative of that inside portion. So that's 4x. So 4x e to the 2x squared plus 5. And then in order to get f double prime, we need to take the derivative of this now, which unfortunately is a product, but it's not too bad of a product. So we take, this is the first, this is the second. So derivative of the first times the second plus first times derivative of the second, which derivative of the second is this, because it's the same exact function. So we would get another 4x e to the 2x squared plus 5. So we have 4 e to the 2x squared plus 5 plus 16x squared e to the 2x squared plus 5. And you can leave it as that, that's fine. Or you can pull out the common factor of 4e to the 2x squared plus 5. And we're left with 1 plus 4x squared as the leftovers in the parentheses. All right, so hopefully pretty straightforward how we take the derivative of the natural exponential function. We're going to take a look at one modeling problem. So look at an example in context. If a person takes a prescribed dose of 5 milligrams of Valium, the amount in the person's bloodstream can be modeled with the following function. So it's 5e to the negative 0.0144 t with t in hours. How much Valium is in their bloodstream after 24 hours? Okay, well, this one, again, they gave us the pieces. We just need to put them together. So we have A of 24. So that gives us that, which if we're looking for an approximate value, it's about 3.5. And that's something you would get on a calculator. Okay, so we can say there will be 3.5 milligrams left after 24 hours. How long will it take for the 5 milligrams to decay to 2.5 milligrams in the bloodstream? Well, longer than 24 hours, right? Because after 24 hours, we still have 3.5. So this time, right, in this previous one, they gave us t. We knew how many hours. This one, it's asking us to solve for t, right? How many hours will it take for our initial 5 to become 2.5? So what are we plugging in here? Well, this is the 5. We're solving for t, and that's the final amount. That's going to be our 2.5. So we're going to take 2.5 equals 5e to the negative 0.0144 t. We'll divide the 5 under there. So that's going to be 1/2. And then e to the negative 0.0144 t. And now if we want to get the t out of this exponent, we need to bring in the natural log. So we're going to take ln of 1/2 equals ln of e to the negative 0.0144 t. ln of 1/2, when you do problems like this with like half-life problems or doubling time problems, you will often see this natural log converted to negative ln of 2. You don't necessarily have to write it like that, but it converts kind of like the one we saw a little while ago with the negative ln of 10 that we did. This one, the L and the E undo each other, so that's negative 0.0144 t. and then divide. T is ln of 2 over 0.0144, which, according to a calculator, is about 48. So we can say there will be 2.5 milligrams left after about 48 hours. That's how long it took for that to cut in half, basically, right? To go from 5 to 2.5. Now we can bring back in the calculus for part C. At what rate is the amount of Valium in the bloodstream decaying 5 hours after the 5 milligram dose is taken? So the key term here is rate, because remember, derivatives give us rate of change. So it's asking for the rate of change, or the derivative, after 5 hours. So let's take the derivative. So we're going to get, so the 5 just tags along. The E derivative is exactly the same, and then just times the derivative of the inside function. So we're going to have e to the negative 0.0144t times that derivative, which is just the number right there. If we combine the two numbers together, we get negative 0.072 times e to that power. This gives us rate of change. Okay, it's asking for a rate specifically after 5 hours. So we take a prime of 5. So that's going to be negative 0.072 e to the negative 0.0144 times 5, which is approximately negative 0.067. So we can go ahead and conclude that 5 hours after taking the 5 milligram dose, the amount in the bloodstream is decreasing by about 0.067 milligrams per hour. So decreasing because it's negative. Okay, this is exponential decay. So the amount is decreasing by about 0.067 milligrams per hour at that moment in time. So the rate at which it's decreasing will change as we go, as time goes on, because this is, again, exponential decay. It's not like linear, where it's just going to keep going down at the exact same rate all the time, right? It's going to drop like that. So initially, it starts dropping very quickly. But as you get further and further, there's less in your system. It starts leveling off how quickly it removes itself from your bloodstream, or how quickly it's absorbed, that kind of thing. All right. But that brings us to the end of section 4 and to the end of chapter 4. So this is our introduction to some more, again, derivative properties, more calculus that we can perform with exponential and logarithmic functions. So I will talk to you all in the next chapter.